transparency. And Dr. Nandedkar, can you see my...
Yes, sir. It's visible.
Yes, okay. All right. Thank you. So it is really wonderful to be meeting with so many biologists, because the main theme of my professional career in statistics is working with biologists. I had first prepared a bunch of slides, and then I attended some of the lectures of this seminar and decided to add some things. So that is why some early slides have the title "Before I Begin." So I want to first thank Nandedkar and Sajid Ali for this opportunity. And I'm quite impressed by the attendance at this workshop. You know, at the inaugural session, at one point there were 450 people enrolled in the meeting. So that is an absolutely remarkable number. Of course, as the lectures continued,
आपण काय म्हणतो ते बोलणारे स्पीकर लोक वगैरे घेतलेले.
ती आपण सगळी सायंटिफिक
भालेराव, पंकज भालेराव, सोनी मॅडम,
अमित सर.
All are muted.
Gore sir, please unmute yourself.
कर दिया आपकी.
So am I audible now?
Yes, sir. Yes, sir. Please go ahead. Sorry for inconvenience.
So I was just saying that at the inaugural function, the number of people attending was 450, and I was very impressed. Then as the lecture started, slowly the numbers started going down, but that is understandable. In any case, the number is very remarkable, and some people at the inauguration ceremony also noticed this, and they said this is a sign of success of this training program. And in a way, I agree with them, but I have a difference of opinion, because I feel it's a sign of failure of statistics people. And why do I say that? Because all these biologists should have been helped by statisticians, and they should not have the need to attend such a seminar. We have statistics teaching colleges and universities all over the country. And if they did their job well, then this seminar would not be necessary. But they don't do their job well. And therefore, the blame is on us. Why does this happen? That the statistics departments in colleges and universities do not seem to help animal science people or pharmacy people or whoever, biologists of all kinds. One of the reasons is that agriculture and animal science people, as a part of their study, have a topic extension works. Whereas science colleges don't have it. They desperately need it. They don't know it. Therefore, I think this is one of the reasons why the statistics people are not in constant interaction with biologists. I heard some earlier lectures, and I thought I should express my reactions to some of these lectures. And the very first lecture by Dr. Abdul Samad was absolutely fascinating for me. So he was very particular. He wanted to talk about his research, but only for bringing out issues that are important in experimental research. For example, bias. These are statistical issues. And he was able to give wonderful examples from his works. And probably the most impressive example that I found was the example of nanoparticle-based rifampicin. And he pointed out that even though there is so much hullabaloo about nanoparticles, there may be limitations of these methods. You know, Indians have a tendency to go overboard. When something new comes, we begin to think that that new thing will solve all our problems. Whereas most things have some limitations, and we have to be very careful about it. And I was very interested to read that the nanoparticle, yes, the nanoparticle-based rifampicin had a problem, that it was not able to handle the small number of pathogens outside the cells. So this was an amazing example, and I hope you all have heard and appreciated his comments. And I wish I could do the same. But I cannot do that because I'm not an animal science person. So where do I get the data? I can only get data from other animal scientists. So I went to Dr. Sajid Ali and said, Bhai Sahab, please give me on loan some data. And he gave data on 2 experiments just to illustrate the points. Now I found that on chat box, many people were asking Dr. Samad about sample size calculation. And in a sense, it is a need of the people, but it was not an appropriate question for that lecture. I thought I will make a couple of comments. So one comment is that sample size is a matter which concerns all of us, everybody who does experiments. But there is that underlying logic for sample size calculations. I think biologists should focus on understanding the logic, and for getting actual number, they should use some software. So what is the logic of sample size decisions? And 2-3 simple ideas. Sample size is the cost that you pay for getting a good result from your experiment. Okay. Now, this cost depends on many things, many aspects of the experiment. Number one, the effect is large, then a very small sample size is adequate. And I will take perhaps a very ridiculous example. My experiment is I have a flame, a burner, and I'm going to take a piece of paper and hold on the flame. What will happen? What is the effect of effect on paper that is held on a flame? Well, the effect is so dramatic and obvious that a sample of size 1 is also enough. Okay. On the other hand, if you have a very subtle effect, does homeopathy help people? Well, it takes a large sample size. The second idea is that if variability in whatever you are measuring is low, then small sample size is enough. If variability is large, then you need large sample size. Again, I am going to take a very ridiculous example. So the question of interest is, what is the difference in the count of legs between cow and chicken? Because I see that people use these 2 animals as very important subjects in animal science. And you will laugh at this question. But if you are talking about new species, you would ask such a question. For this question, a sample of 1 cow and 1 chicken is enough. Why? Because as far as the number of legs is concerned, the variability is almost zero. Almost zero. In a million cows, there may be 1 odd cow with a 5th leg. But it is so rare that newspapers will immediately print a picture of that cow. So by and large, there is hardly any variation. So when there is less variation, less small sample size is enough. As variation goes up, sample size requirement goes up. And the last thing is, whatever you are studying, if you want higher precision, then you need larger sample size. If a crude measurement is good enough, then a small sample size is enough. So these are the basic ideas. They work everywhere, but for any specific problem, you will have to use the software to get the sample size for your experiment. Then a comment about Dr. Gore's lecture. I found his lecture very impressive. He said many interesting things, and I will pick up 1 or 2. What he taught us was of immediate use. And one point he made was that Excel is a very powerful software and extremely underutilized. Very few people really use abilities of Excel. So my recommendation to you is, the first thing, whenever you are stuck in calculations, first thing is ask Google if that can be done in Excel. And Google will often tell you simple ways by which Excel can do the job for you. Another thing that Dr. Gore said was that Indian research is similar to work outside. But Indian research often does not get accepted in good journals. Why? Because Indian animal scientists, Indian biologists are weak in data analysis. But that is very sad. You are good as scientists and you just need help in sorting out data. And that is where statisticians should be more than happy to help. I think this deficiency can be corrected, and you should be in a position to send your papers to high impact factor journals. How do we do that? By collaboration between biologists and statisticians. So I would recommend to you, look around a nearby university, nearby college, and if there is an enthusiastic statistics teacher, maybe he will or she will be able to help you. And of course, you know, for agriculture people, the Indian Agricultural Statistics Research Institute in New Delhi is also available. And one of the faculty members there, Dr. Rajendra Prasad, will be talking to you, I guess, tomorrow. So that is another place where you can approach. But I think the best solution is local answer. If this does not work, temporarily, you and I, we can work together. You can write to me, and I request you, please note my email address. You can write to me anytime, and I will be happy to respond to the extent that I know. But I think we should try and overcome this limitation and aim at, we should be ambitious. We should aim at getting our papers published in well-known international journals with high impact factors. And that is one of the best things that statistics can help you in. Even the speaker who will follow me is also a statistics teacher, and you can ask her. Okay, so let us be clear about why. Let us remember, I have worked with biologists all my life, and I know that many of them are very tired of statistical analysis and stuff like that. But we still have to do it. Why? Because we want to publish in good journals. So that is an immediate reason. But a more profound reason is we all want to know correctly whatever it is that we are searching. So if I am doing a drug trial, is the drug effective? And I want a real answer. Okay, I don't want an answer that will make me happy. I want a true answer. Sometimes I want to predict what will happen in future. All this can be done with statistics. How do we start? And I hope I will be able to demonstrate these things through some preliminary analysis of the data that Sajid Ali Sahab has given to me. But the first thing to do is draw graphs. Always summarize. Look at summary and descriptive statistics. I think Dr. Gore taught us how to get descriptive statistics using Excel. Very simple. And look at them and try to make sense of what those numbers are saying. Oftentimes, we use software and produce numbers, and we pay less attention to making sense out of those numbers. Now, that is a very wasteful use of software. Dr. Gite pointed out something important. He said, what is the research question? So let us keep our research question in mind all the time. Here is my favorite thing. I want you to understand the difference between discovery and confirmation. Statistics is used in both, but it is used somewhat differently. What do I mean by discovery? Remember, discoveries can be made in many ways. They say that Ramanujan, the great Indian mathematician, discovered new results in mathematics in sleep. And he said that Devi Saraswati or somebody, in dreams tells him mathematical results, whatever it is. He got those results anyway. So you can dream about them. There was this chemist, I forget his name, but in sleep, he dreamt that a snake was swallowing his own tail. And that gave him the idea of a structure for benzene, C6H6, and he then created a ring. So that ring was the first time proposed by this man, and he said, I dreamt about it. When it comes to discovery, it does not matter how you discovered. As long as it is true and useful, people won't ask how you did it. On the other hand, if you have a result, but you want to confirm it, then you want all the power of statistics. Statistics has the role of an auditor. You know what an auditor is? Auditor is one kind of accountant. He's also an accountant, but he's supposed to find loopholes. So statisticians must play both roles. As accountants, they will try to help you with analyzing data, and as auditors, they will try to tell you the weakness in your data. Okay? So for discovery, don't bother. Do anything you want. Once you discover a result, you have to confirm it using a good enough experiment, and then all the rules of statistics have to be applied. The next thing is, I shared a message with participants. If you feel you can write to me about your difficulties, and I will talk about them in the class. And 3-4 of you wrote to me, and I wrote to them the responses, and I will share those responses here. So the first one was this lady Mamata Kumari. And before I tell you her question, I want to make a comment about her name. I think she spells it with M-A-M-T-A. So it sounds like Mamta. And I have a bit of an objection to that spelling because Mamata is a name that comes from the Sanskrit word mama, which means my own. You know, it is about ownership, intimacy of relation. And that mama, second M is complete, not short. Anyway, it is just for fun. So what did Mamata ask? She said, I have two samples. One data set follows normal distribution, other data set does not follow. Because people have given the rule, if both the data sets follow normal, use t-test. If they are non-normal, use non-parametric test. But if I have one normal, the other non-normal, what to do? Precisely. Things fall in between explanations given in the textbook. And that is where you need a counselor or a helper. So what did I write to her? I said, this is a very good question. The t-test is robust. What does that mean? Robust means it is not terribly sensitive to data variations. So even if there is a little bit of non-normality, it doesn't matter. T-test will still do a good job. Okay. Whereas if something is terribly non-normal, then you better use man-Whitney test. Even though one set is normal, you should use man-Whitney test. I think Dr. Gite taught you yesterday how to do the man-Whitney test. But I have a third comment. The comment is, please do not overestimate ability of statistics. Statistics is able to tell you differences when most other things are similar. So when we compare two samples, generally we are talking about similarity of the mean or similarity of the median, but all other things are supposed to be given to be similar. So if one is very, very normal, the other is terribly non-normal, then maybe you should think more about the research question. Why are these? Because if you are measuring the same thing under two conditions, why are you getting terribly different distributions? It's a deeper question. Okay, so I have a formal answer and I have an informal advice. The next question was from Mr. Chopade, and he said, can you throw some light on principal component analysis, its purpose, its utility, and how to estimate? So, of course, this is an advanced topic, and this is the problem of seminar like this, that the participants have great variation in their background. So, this person obviously uses all the basic statistics and is really worried about a complex multivariate analysis tool. Okay, whatever it is. So, here is my answer. So principal component analysis is for situations when you have too many variables and too many measurements, and it is difficult to work with them. It reduces variables by creating new variables. Fewer. If you started with 10, now it reduces to 3. Okay, and these are linear combinations of original variables. And this approach doesn't work always, but sometimes it works. When do you say it works? When one or two or three components together contain all the variation in the original. How to check it? All that will be in the software. Ideally, if two principal components contain most of the variation, that is excellent, because then we draw an XY plot and see the pattern in the data. Okay. An example, I have given a reference to a paper by Raghavendra Gadakkar. This is a great scientist. He was president of the Indian National Science Academy. He's one of the most celebrated animal biologists of India. And he has an outstanding web page on the Indian Institute of Science website, and you should be able to read his paper. So what was that paper? So he measured, what were the variables? He had lots of variables, right? He measured various activities of wasps. So how to classify wasps based on activity budget? So a wasp sometimes does nothing, sometimes goes out for foraging, sometimes fights with others, sometimes eats, whatever, any number of variables. In this case, it turned out that first two components together were quite adequate, and he plotted them. And he found that the wasps fell into 3 clusters, and he could interpret those clusters. He called one group sitters, the second foragers, and third fighters. In ants and bees also such castes are known to be present. There are some fighter ants and so on. There is a queen ant, of course, there is a queen bee, but these are genetics and morphologically identifiable. Queen bee you can recognize because it is much bigger than other bees. Fighter ants you can recognize, they are also bigger and so forth. But in paper wasp, there is no such morphological difference. So he called them behavioral castes. So this was a great leap forward. This paper became very famous, you see. Now, as far as actual implementation is concerned, this is not something you can do without good software. So you have to use a software, and somehow you have to manage it. So in this case, if you are not able to do, maybe I can help. Okay. Next, there was this lady. What is her name? She said, please focus on application of various statistical tools rather than going through formulas. I fully agree with her. Formulas is not something we should worry about. They are in the book. To know where and how to use the tools, and most importantly, how to draw inferences from. So please don't go into details of formulas. Just focus on where to use each method. And I agree with her. So I promised her I will try to do that. I'm going to try it, but there is a limited time. All right. Now, yet another person asked this question. Please demonstrate how to select a statistical test with suitable examples from veterinary field. For example, I have a treatment group and a control group, and I have measured 4 parameters: body weight, girth, length, and height in both groups. What test will I choose? And I wrote back an answer. I said, this looks like a 2-sample problem. You have a control group and a treated group, and maybe you are asking whether body weight goes up. We are going to look at such a data. Chicken are being fed. Does the body weight grow more with better diet? So you take one parameter at a time, say body weight, and carry out a t-test. Okay, so you'll have 4 t-tests. The parameters are such that I think they will all follow normal distribution. I would be very surprised if the distributions are not normal. Sometimes a distribution that is not normal can be made into a normal distribution by doing what is called a transformation. We won't go into that. But I suspect that these measurements may be correlated. So I am asking her, please calculate correlations among them. And you, let us say height and length and body weight. If these are highly correlated, then probably you can use just one of these. Okay. Otherwise, you want to use all 4, then you need a multivariate test. And again, you will need software to do that. Yet another method I will only mention, not go into it. When you do repeat analysis on the same data sets, you have a problem called multiplicity. And there is a method called Hochberg correction. And she can think about it. It's easy to read. You can get all this information on Wikipedia. The question, tell us which test to use in which situation, is like going to a doctor and saying, tell me which medicine to use for which situation. Bring me that situation, I will recommend a medicine. General answer is very difficult. It depends on the situation. All right. Then Dr. Sajid Ali said that I should cover principles of design of experiments, mainly importance of replication, randomization, and local control. And I'm going to do that job in 2 minutes. So first is replication. Replication is more number of experimental units per measurement. So we should increase the number of observations to make results more reliable. This is the principle. Now, exactly how much to replicate is a sample size question, and we won't go into that. What is local control? If you have experimental units which are not alike, then split them into groups. So if you have cows, you say, for each breed, I will do the experiment separately. If you have different ages, the young ones, heifers, adults, etc., have to be treated separately. If you have male and female, then treat them separately. This is called local control. Very simple. And instinctively, all good experimenters do that. They don't have to be taught this. Randomization, this is a bit of a technical thing. And when you have an experimental unit in which treatment to give, don't decide that in an ad hoc manner. Try to use some kind of a coin tossing thing, some kind of random number tables. This takes care of bias. Otherwise, you can have problems. There is one more thing which he has not mentioned, because I am very much in human clinical trials. We use something called blinding. And I'm sure in animal trials also, blinding can be useful, where the experimenter should not know which is the treatment and which is the placebo, because otherwise he begins to read what is not there. Okay. Then during the lecture of Dr. Gite, people saw the display on screen and they asked, and I could see in the chat box this question: please explain the use of Levines test. But he did not have time. I think he had a meeting with the chancellor, vice chancellor. He ran away naturally. His time was up. So I thought I will mention very briefly what is the use of Levines test. So we were earlier saying that a t-test for comparing two groups assumes that most of the things are similar, only mean is different at all, if at all. So it assumes that variances are similar, and Levine's test tries to check, in fact, if the variances are similar. Okay. If you are in ANOVA, that is, you are comparing three or more groups, again, the assumption is that the distributions are similar and variances are also similar, and Levine checks that. So what if Levine says that variances are not equal? Then it would be better to check if there is a method for comparing two groups without assuming variance equality, or some, you have to take some care. Okay, it's not a trivial job. So Levine's test alerts you whenever you need to do something more than just applying t-test. It will alert you. Then in the chat box, I think in whose lecture I don't remember, but people were saying, please recommend some books to us. So I'm going to recommend books, and these are, or most of them are not textbooks. They are books which are readable and provide insights. So first book has a funny name, How to Lie with Statistics. And the name of the author is Darrell Huff. It's a very old book. I think it has some new edition. And it tells you about many interesting things that go wrong in statistics. For example, mean or average. And what is its story? He says there is a visitor to Arizona. Arizona is a province in the United States, and it's a desert. I used to live and work in Arizona. So in summer it is very hot, and in winter it is very cold. Okay. So he asks people, how is the weather here? Oh, they say average temperature is 60 degrees. Oh, that's a very pleasant temperature. This is Fahrenheit. Americans still use Fahrenheit. 60 degrees is a very pleasant temperature. And then he realizes this average is a useless number, because half the time the temperature is 60 degrees Fahrenheit, and half the time it is boiling 90 degrees Fahrenheit. So if there is too much variation, then mean does not have any use. Okay, we tend to miss this fact, and he tells you
I think Dr. Gores sir lost the connectivity. Please wait. Dr. Gore sir is facing internet problem. He will join soon. Please wait for a moment.
Okay, can you hear me now?
Yes, sir. Yes, sir. Please share your PowerPoint.
Yes. Do I have to start video, isn't it? Yeah. Okay. I need to share and you have to help me with that. Please give me right to share.
Yes, sir, you can say, sir, I think from your name, 2 more participants have joined.
Ah,
Amit, make current ID as a co-host.
I made sir co-host.
Okay. Yes.
Okay, sir. Full screen, please.
yeah. All right. Sorry about the disruption. I don't know what went wrong. I got disconnected. Can you hear me now?
Okay, sir. Okay now.
All right. So I thought I will recommend some books, and this first book is How to Lie with Statistics, and it is a very humorous book, but tells you important things about statistics. And the second is Facts from Figures by Moroni. Third is Naked Statistics, and this has become a hot sale item. I think all these are available on Amazon. Yet another one is Say It with Figures, and it tells you how to use these contingency tables. And these are very, very readable books. They don't tell you formulas. They do tell you where to use what. And now I'm going to mention 2 textbooks. First is Statistical Methods by Snedeker. One of those books written by 2 of the most well-known statisticians in the world. None of them is alive anymore, but the book is very much in use. Similarly, this is a very nice book about non-parametric statistics. And I think all these are available on Amazon. Okay. Now, these are the slides I prepared while I watched all the earlier lectures. And now I go to the slide that I had prepared for my own lecture. And as you can see, I was trying to tell you that, of course, experiments are the heart of research. And I have borrowed 2 data sets from Sajid Ali, one on blood chemistry of cattle and the other on growth of poultry. And what is it that people want to do in most of these experiments? They want to compare treatments. They want to compare time points. They want to study interventions. These are very broad things. And why do we need statistics here? And we will talk about that again and again. And biologists are often afraid of statistics, which is quite unnecessary. We should start with graphics like histogram and normal curve and stuff like that, and I will do that. And box plot, I thought nobody mentioned box plot. This is an absolutely wonderful tool, and I want to tell you about it if you don't know. And we have to study variability and coefficient of variation. Some of these things, Sajid Ali Saab said I should talk about, and I will. Variability is the heart of the problem. What is the problem? The problem in biological experiments is that results are not easily replicable. I think Dr. Samad pointed this out, that you do an experiment, you get a result, but somebody else doing the same experiment in another laboratory, in another country, at another time should also get the same result. In biology, this is very difficult. Okay. 2 individuals born of the same parents are also different. Same farm, same variety of crop in different, and one half is to the left and one half to the right, and the yields are not the same. There is variation in biological readings for which we do not know any reason. Okay. Statistics is for separating variation for which there is a reason and variation for which there is no reason. Okay. That no reason variation is what we call chance. Tera nasib bekar hai, kya karenge? So we have to study variation. And coefficient of variation is a very useful quantity. We'll talk about it. And comparison is the most important thing in an experiment. So comparing two means t-test is very important. Comparing many means ANOVA is very important. The last thing I will mention is studying trends, forecasting. So this is regression. And again, Dr. Dept talked about regression in his lecture. So this experiment was on blood chemistry. This is a phrase you should remember. Statistics is what statistics does. So if it does not give you results, then it is useless statistics. Okay. I don't mean results that you want. I mean good analysis of your experiment. So I find that when I interact with biology, there is no point in teaching theory and mathematics. That can come much, much later. For people who use a lot, what we have to do is to take data and see what to do about it. This is the question somebody asked, and I fully agree. So what was the data in this cattle blood chemistry experiment? They were measuring chemicals, 4 different things. They had 3 treatments, and there was measurement with and without ultrasonography. Now, these are things I don't understand, but presumably measurement was done in 2 different ways. Okay. There were 4 time points: immediately after intervention, 1 day after, 24 days, 48 days. So this is very common feature of many animal experiments, many clinical trials, everything. And they were studying 4 chemicals. Just as this lady in Kerala had 4 parameters. These were 4 parameters. And I want to show you, this is a bad slide because when I pasted it on the PPT, I realized that the font is very small. When I increase the font, I could not expand the column width, and so it looks very funny. But the point, what is the point? I want to show you, the first column shows that there are multiple treatments. Second column shows that there are multiple time points, 0, that is immediately after intervention, 1 day, 24 days, 48 days. And the next 2 columns are for a particular chemical. That also I missed. The first one was, and last one is creatinine, I remember. Others were short form, so I didn't know. So you have 2 measurements, one without using ultrasonography, the other with ultrasonography. All these things are decided by the experimental biologist, not by a statistician. All right. So what do we want from this game? We want comparisons. Comparisons between time points, comparisons between treatments, comparisons between 2 methods of measurement, and so on. Among treatments, among time points, and 2 methods of measurement. And this is to be done for each chemical. How to compare? All this comes without technical statistics. Many biologists I talk to, as soon as they think of data, they immediately want to go into statistics. And I say, no, apply your own mind, apply common sense. And I want to show you how to apply common sense. I mean, as soon as I say it, it will be obvious to you. See, there is no need to be afraid of statistics. The fear for statistics comes from 3 reasons. One is people are afraid of complicated formulas. I understand. I am also afraid of complicated formulas. And then there is computing involved. I am not a computing person. I hate it, but kya karenge? You have to do it. And third is conceptual confusion. Out of these, first handle. Don't memorize. Always look at the book. Okay. Computing, just learn how to use a statistical package. And I hope the way Dr. Gite showed you how to use SPSS, you will see that it is not difficult. I assure you, I am not a computing person. People confuse. People think if you are a statistician, you must be very good in. I belong to the older generation. In my time, there were no computers. I never learned computing. Now I manage, but I'm not very good at it. So you don't have to be good at computing, but learn basics of what you need to do. Now it is the concept which you have to learn. And I think it is not difficult. Okay. It is a bit, and the logic of statistics is somewhat unfamiliar, but you will get used to it. So I'm going to not give you a lecture on logic, but show you how to apply common sense for comparison of measurement with and without ultrasonography. Okay. Okay, here is again, this slide is very bad by my standard, but again, I am not terribly good at manipulating things. But you see, on the first column, you have the treatment, second column time interval, next third column measurement without sonography, and fourth column with sonography. What is it we want? Does sonography change the measurement? क्या करने का? Look at the numbers. Look at the numbers. Very first row, what are the readings? 82.3, 112.6. See, supposedly the treatment is the same, time interval is the same, then the two values should be same. But they are not. The ultrasonography value is higher. And if you go down the line, in this set of numbers, everywhere ultrasonography gives you a higher value than non-ultrasonography. That is the difference. And I don't need to be a statistician to recognize it. I can see it. I hope you all can see it. All differences, if you take the ultrasonography value, subtract the without sonography value, the difference is positive. Sonography wala measurement bada hai. You don't need statistics for this. Throughout it is happening. All ultrasonography readings are larger. So I can draw a conclusion that ultrasonography se higher value milta hai. Nothing wrong with it. This is what I mean by applying common sense. Okay. So was that difficult? I think it was very simple, very simple. It's not always like that. I have artificially created a data set here. But now let us bring in difficulties. First difficulty is if I had only one case and ultrasonography value is higher. So kya karenge aap? Will you agree that with sonography value goes up? No. Ek se kya hota hai? One is not enough. Nobody will accept this. You try it again, show it again. See, people don't call it replication, but they know it. Everybody, all good scientists know that you need a bunch of measurement, not just one experiment. Okay. So how many do you need? That's a technical question. And I'm going to give you the logic of how we do it for a very simple problem. The intuition is if one method always gives higher value, it's a better one, or it gives higher value. Usme kya hai? Now I'm going to take a coin toss problem. Find out coin fair or biased. Cheating hai ya fair अच्छा चल रहा है. Where do we use coin toss? Either in statistics books or in cricket match. So we will not forget about statistics book, cricket match. Suppose in a series, Indian captain always wins the toss. What will the opposition say? The other people will say, कुछ गड़बड़ है. They are using a coin which always gives it. पहले चेक करो दोनों साइड को हेड ही नहीं है ना. That is the first thing, but that obviously is too much. If one side always gets the right answer, you begin to suspect that the coin is biased. How to check? This is a statistical question. This is a research question. Is the coin fair? Is the coin unfair? Okay. Is the coin biased? All right. When do you say it is biased? Now statisticians have a rule. If 7 tosses in a row give you always head, gadbadi. Where do they get 7? 7 किधर से आया भाई? 6 काफी नहीं है. So here is the logic. If you toss once, what is the chance of getting a head? 50%. What is the probability? Half. If you toss twice, what is the chance of getting head followed by head? You multiply. Half into half is 1/4. What is the chance of getting 7 heads in a row? Half raised to power 7. That is 1/128. This is the first time the probability goes below 1/100. समझे क्या? And we have convention कि 100 में एक, इससे भी कम अगर probability है तो गड़बड़ है. If it was a good coin, then 7 in a row would be very, very unlikely. This is the logic. Okay. So such is the logic that we use. Implementing it in complicated situations is not easy. You have to use the software. So when we see something for which our chance is less than 1 in 100, we say kuch gafla hai. Something is wrong. Statistics cannot tell you what is wrong. It will tell you isme dekho. So why do we need statistics? To quantify common sense. Common sense is easy to apply in simple cases. In complicated cases, it is not. To create tools for complicated situations. And typically your experiments are complicated, boss. You are not easy people to help. And what is the problem? The basic problem is variation. Your values are not replicated. Same thing you do again, you don't get the same value. Okay? This is called the problem of variation. There is a lot of variation in biology. It's not your fault. So whenever, suppose I give as a young man, I did an experiment. I was involved in an experiment of food supplement. I think it was Shaw Wallace company or something. And we were going to add that supplement to the diet of buffaloes. Question was, when will you say that the supplement has led to additional milk yield? So we would say, well, you have to compare with control and everything is variable, etc. So small differences, people can say, no, it is just chance. At what point you say this is not due to chance, it is due to the treatment? This is the question that statistics has to answer. So we make precise rules. And what we did were the data set, sonography and so on. It's called sign tests. So if you take the differences, how many are positive, how many are negative? If too many positives, we say whatever is happening, first value is bigger than second. If too many differences are positive, we jump to a conclusion. This is how statistics logic works. All right. What time is it now? I have taken 1 hour already. I have 1 more hour. I think we are doing fine. So everybody talks about bell curves. So here are some pictures of bell curves. And we should have an idea of what mean and variance mean. So the blue curve, if you can see my cursor, this one is the blue curve, is a thin and tall curve. So that means variation is low. Okay. The brown, where is it? Yeah, this is the one. The brown one is very well spread out and short. So it is fat and short. So when it is short and fat, it means variability is high. Okay. Next green one. This green one has variability in between the brown and the blue. But its mean is different. Its mean is -2. Brown and blue have mean 0. And what about the red one? Red one has also 0 mean, but its variance is bigger than the variance of the green and smaller than the variance of the brown. So when we talk about variance, these pictures are what we should have in mind. What does it mean for some data set to have a larger variance? That means it is well spread out and short. So this is how you should get an intuitive notion of the idea of variance. Don't go by formulas. I understand formulas are problematic, but if these pictures are before you, then you will understand things easily. Okay. Now here I have 2 normal curves. Oops, what happened? Now there are only 2, and this is the blue curve, and this blue curve has small variance. It is more compact. It has less spread, whereas the dashed curve has high variance, and it is more spread and it is short. So variance low means values are close to each other and values are close to the mean. Variance high means values run away a lot from the mean. Now, for the biologist, in mathematics, there is a theorem. It is called the central limit theorem. Okay, what does it say? It says that if you have many measurements, then their average tends to have a normal distribution. How does it translate to genetics? So we say, if we are talking about a expression which is polygenic in its inheritance. Lots of genes, each individually contributing a little, and total of it or average of it comes out as a phenotype. Then that phenotype is likely to follow a normal distribution. So the human height follows a normal distribution. That is the idea. And this picture is supposed to help you understand. So what is this picture? These women are sorted out by their heights, each group, each row. So in front, on the left-hand side are the short girls, on the right-hand side are the tallest girls. And in the middle, there are these average height girls. And average height girls are followed by average height girls and whatever. And you see the frequency of average height girls is the highest. Frequency of extreme height girls is the lowest, and something in between. So this picture to me is a biological depiction of the bell shape. Okay. All this is available on the internet. You can easily locate this. Now the question is, are all variables normally distributed? And the answer is no, there are some variables which are not normally distributed. An obvious example is gender of a newborn, male or female. That's not normal distribution. And we're interested in number of female cows. You know, yesterday there was talk about sex selection and all this. We want cows because we get milk from them. And bulls are not all that useful. In earlier days, in the ancient times, bulls were our traction. All the plowing in hard soil could be done only with the help of bulls. Now that role has disappeared. Everybody uses tractors. So males are of very little use. This is in fact true in general. Males play a limited role. It is the females which are the productive part of the population. So the distribution of number of females is not normal. It is binomial anyway. We won't go into detail. Take the example of length of life. We are all interested in this variable. And this does not follow normal distribution. It follows a very positively skewed distribution called Weibull distribution. And who is interested in it? Insurance people are interested. They want to know, because they have to calculate the probability of an animal dying in so much time. And on that base the premium. Okay. So not everything is normal. Very important things are non-normal also. Now this is a hypothetical drawing. We are talking about height of humans. And we have the height of men, height of women. If this is the true picture, what does it mean? That men and women, their heights have similar variance, but men have height much bigger mean. How much bigger? So much so that there is no overlap. It means every man is taller than every woman. This picture essentially depicts such a situation. Here is another picture. Here, both have normal distribution, but every man taller than every woman? No, not true. For example, this blue region, men are shorter than women. Isn't it? Yeah. And after that, everywhere, women are shorter than men. So, this second picture is what is the reality. Okay. Do not expect your intervention to lead to the first picture kind of situation. Most of the times in real life, you will be seeing this. Okay. So, reality is overlap. That is why we have to sort out the reality using statistics. So, left picture says variability is low, means are highly different, therefore the curves become non-overlapping. Right picture says mean variance is higher and differences in mean are smaller. When that happens, there is lot of overlap. Okay. All right. So let us go to the poultry data. What was this data about? It was about growth. And some, I don't understand what 309 is, presumably some whatever vitamin. And they started with 1-day-old chicks. And periodically they were weighing every chick. And And at the end of that experiment, you slaughtered some chicks and found out weight of whatever. Okay. So there were 3 groups of 20, and these 60 birds got one treatment. Okay. Fine. This was the funny part of that experiment, that they did not know individual ID of a bird, and therefore you had a list of 20 weights, but which one belongs to which bird you don't know. So I asked myself, why is this happening? And then I thought maybe it is not easy to tag individual birds. But if you have heard the introduction that Dr. Nandedkar gave for me, he said this man is associated with used to be associated with the Bombay Natural History Society. Incidentally, that introduction was a bit too long. I think we should be very brief about introductions. Anyway, so this question of individual tagging of birds is very much very important for the Bombay Natural History Society. So why is an individual one-day-old chick not ID'd? Because BNHS people do it all the time. We can keep an ID on tiny birds. What is the ID that they use? They have a tag, numbered tag. Okay. Now this is a tiny bird. What is its name? It is called pale-billed flower pecker. What is this weight? 15 grams. So this is less weight than one-day-old chick. But such birds are studied by BNHS, and they do ring them. And the birds come in different sizes. Vulture is in kilograms, so it has a big leg, so it has to have a bigger ring, and so on. But all this is possible. So point I'm making is this has nothing to do with statistics, or at least there was no question of individual growth curve. Otherwise, I would have said you have to have ID before you can draw individual growth curves. So if you don't ask question about individual growth, then it is all right. But generally, you should have identity of each individual experimental unit. Or maybe these rings are not cheap and they are imported. So maybe that is the reason. Okay, whatever it is. This is a minor point. So now I said that we should always start by drawing graphs. So what is A1? A1 is one group of 20 birds. And the weights are given. So I draw a histogram. So what you see here is called a histogram. Okay. And then I have superimposed a normal curve on it. I say I have means the software has. Incidentally, the software that I am using is called Minitab, because the first time I went to teach in Canada, that was 1984. They used to use this software Minitab, and I had to learn it to teach my students. And Minitab has been around, and it is as popular as SPSS and so on. It is as expensive as SPSS. And therefore, I don't recommend this to people. But I was very, very happy to hear one person in your audience explained that there is a free software available, which is called PSPP. So I went to the internet, I checked, yes, it exists. Nice links are available. Please read it. If possible, download it, learn how to use it so that you don't have to pay money for SPSS. Okay. Or Minitab or anything. I just happen to have Minitab, so I'm using it. Anyway. So the question is this weight distribution normal? इसको देख के बोल सकते हैं क्या? I can say yes, you can say no. Is there an objective way of deciding? And there is. So there is a statistical test available. And I will not explain how it is done. I will just show you the graphical presentation of it. Oh, here is another group. Does this look normal? Is it more normal, less normal than first one? These are the questions that we want to ask, because if two groups are to be compared, you are going to check normality of each. All right. So this is what Minitab gives you for comparing normality. The idea is that straight line, all the points should be close to it, and there is something called the p-value here. I don't know if you can see it. The p-value is 0.865. This is for the first group. It is point. So if p-value is large, it means the fit is good. It means the normality assumption is reasonable. Okay. All right. Whereas if that p-value is very small, then you should not accept normality. All right. This is the simple rule. Now I want to create. Like I said to that lady that your weight and height and things like that, they are polygenic. And I think by and large, they will be normally distributed. But now as a teacher here in this class, I want to show you that this tool actually is good. Meaning if you give it really non-normal data, it will declare it as non-normal. So I want to cook up non-normal data. How did I do that? See, Sajid Ali Bhai gave me weights at 1 day old, 1 week old, 2 week old, 3 week old, etc. So for the same birds, I took 1 day old weight values and 1 week old weight values and added. Nothing nonsense. I'm just trying to create an obviously non-normal data. Okay. Look at the histogram. Bloody hell. Obviously, there are two groups, boss. No way it is normal. Okay. We know that. Now let us see what the tool does. Clear indication of two groups. Look at this graph. So firstly, those points are very funny. They are supposed to be on that blue line for normality. And the p-value is also very low. Okay, then it is not normal. So this is how you check p-value. Some version of this will be available in whatever software you are doing. So the data are created because you know what is not normal. And the tool also gives that answer. All right. So what is it now? A first group of 1 day old chicks, and that A1 group, a weight of 21 day old chicks. Oh, this is now descriptive statistics. And you can get a whole lot of things, and I have only taken out a few. So N is, that is the total count, average 40.25 grams, standard deviation 2.845. Okay, minimum 35. Good to know what is the minimum. What is Q1? Q1 is a value such that 25 cases are below. What is median? Median is the value such that 50% cases are below, 50% cases are above. It's like median of the road. What is Q3? Q3 is the value such that 25% are above, and then maximum. All right. All these things you can get from Excel very, very easily, as you have seen earlier. Now, my favorite thing, box plot. I think others earlier did not talk about it, which surprises me. It's very easy. So again, the software has drawn this box plot. What is this box plot? You see, each is a box. Huh? So first is A1 is the group of 1 day old chicks, A2 is the another group of 1 day old chicks. And there is no real big difference. They are randomly chosen from a pile of 1 day old chicks. Okay. Now, what does the box plot show? See, this line is a median. So here the median is about 40. And this is Q1, this is Q3. Okay, these are the things, and it gives you some idea of variability. If the spread is very big, we can see it in the picture. And this is again median of the second one. How much is it? Probably 38, 39, something like that. Okay. So box plot is very useful. It shows median Q1, Q3. It also shows variation. And it shows outliers. This one, outliers are shown as points separate from the rest, and they are starred. This, obviously, this data set doesn't have outliers. What do? I create artificially outliers. So what I did was couple of numbers obviously larger than that value, and then drew the box plot again. But right now, there are these two groups, and do they look similar? Well, this group has 40 as its as median. This group has a slightly smaller median. So the question is, are the two groups similar? Second one is lighter in weight. This is the question. Is that difference due to chance, or is it because that somehow that A2 group is thinner? We know in this case that there is no reason, they are randomly selected. So this has to be due to chance. Will our tool show that? This is the question. Okay, so this is where we will use a t-test. Okay, all right. Now what I did was I added, see, these are, median was 40, maximum, what was the maximum? Here is the maximum. Or maybe in the previous slide. Maximum was 46. Okay. Now I added some 100 or something, obviously. So I added two numbers. One was 125, another was 140, and drew the box plot. This is the box plot. I know there are two outliers. They don't belong there. So this tool will point out such funny cases. If yesterday, or in earlier lectures, lot of people used the word outlier. And I think even the question of what to do with outliers also came up, and I want to add to that discussion. So firstly, when there are outliers, you have to ask yourself, are these exceptional individuals or something else? More likely, this is a copying error, data entry error. First check. Okay. If you cannot find any experimental error, then you say, why are these two fellows with such great weights? Sometimes you have explanation. In clinical trials, we do not allow people to simply remove the outliers, because then it may be that people do things, manipulate data so that their drug is shown to be effective. So whenever you have outliers, check whether there are errors, obvious errors. Then check whether there is a reason why they should be high. And ultimately, you will have to take responsibility that I am satisfied that there is something wrong here, I am going to remove. Okay. So if I am analyzing your data on a clinical trial, I will say, boss, these are outliers. You have to certify whether they are genuinely mistakes or something to be removed or to be kept. And in fact, what we do, see, when for drug reports, they go to the FDA or drug regulator, we analyze with and without outliers. So we don't eliminate. Now I'm going to take an example for box plot, which is totally different from animal science. But it is something that you and I, we all experience. This is about state transport buses. And what is the variable of interest? Diesel consumption. Okay. What is the common thing about state transport buses all over India? All state transport companies are in loss. Maharashtra, where I live, big loss. Most, if you tell me a state where it is not in loss, that will be a wonderful news. But most of the states are in loss. So what do they need? They need to find ways to save money. Okay. If less diesel is needed for traveling the same distance, that is saved money, right? How do they measure? They have this thing called kilometers per 10 liters, KPTL. Okay, this is the variable, and they have records of that. A lot of data is available. And I'm going to show you one illustrative data set. So this is in, near where I live, two little places, Phaltan and Baramati. So buses traveling between those two. And what was the KPTL? So there was a lot of KPTL values. I drew the box plot. There are three outliers. What is the importance? In this case, we are sure that there is no data entry or nothing. What is the importance of these stars? These stars, remember, what is the average here? About 50 something, 52, 53 kilometers in 10 liters. And this lower value, this is 40. So he lost 10 kilometers. Okay. Out of 10 liters. So median is about 52, three outliers. Who are these? Who drove those buses? Which were those buses? These are the investigations that we carried out. We found that in that particular depot, Baramati depot, there was a bus. And I have the idea of that bus, that's the registration number. That bus, whenever that bus ran, the KPTL value was always low. What does it mean? It means that that bus has to be repaired, engine has to be overhauled, tires have to be replaced, or the bus has to be scrapped. Outliers are supposed to give you actionable suggestions. Okay? All right. This curve is supposed to explain what is variance, at least for the normal distribution. So I think such picture was shown earlier also. So this is a normal curve, this is the mean, And if you go one standard deviation, sigma is the Greek letter used for representing standard deviation. Mu plus sigma to mu minus sigma is about 68%. A mu plus 2 sigma to mu minus 2 sigma, that contains about 95%. So outside of mu plus 2 sigma, mu minus 2 sigma, only 5%. Outside of mu plus 3 sigma and mu minus 3 sigma is really 0.3%. What does it mean? If I find standard deviation useful for data with normal distribution, we can tell how far the value is likely to drift. Okay. If it drifts more, there must be a reason. That's an outlier. Okay. So what we do is we take the value, subtract the mean, divide by standard deviation. This is called the Z value. And if Z value is bigger than 3, kuch gadbad hai. If Z value is less than minus 3, kuch gadbad hai. This is called standardization. Okay. Now I want to talk about coefficient of variation because it is very widely used. You should know what coefficient of variation is. What is its importance? Remember, you have all studied physics and chemistry. What is the coefficient? Coefficient is a dimensionless quantity. Okay. Somehow, without context, it tells you something about the phenomenon. All right. So, first row is data of weight of one-day-old chicks in grams. And second row, same data in kilograms. So, I have to divide by 1000. So, the information is identical. Okay. What happens to means and standard deviation? Look at this. In the first case, mean is 2.33. I think my naming, I'm very sorry about this confusion. See, data entry error. 39.2 is the mean and 2.39 is the standard deviation. I think I must have done the mistake. Nobody else is responsible for it. Whereas when I divide by 1000, give it into kilograms, then the mean becomes 039. Standard deviation also becomes different. Okay. So what is the message? The message is, oh, I am very sorry about this confusion. I am responsible for it. If you change the units of measurement, then standard deviation changes. Okay. But take the ratio. What is CV? CV is standard deviation upon mean. So this is 2.39 upon 39 or 239 upon 039, and the ratio is the same. Okay. So the most important property of coefficient of variation is it is unit free. Whatever the units in which you measure, coefficient of variation is not affected. Mean and standard deviation do get affected. So this is the coefficient of variation, 0.061, etc. Generally, it is expressed as percent, multiplied by 100. So the coefficient of variation is 6.1%. Okay. So this is the great use of coefficient of variation. Standard deviation changes with unit, but coefficient of variation does not change. Coefficient of variation is unit free. Why am I pushing this? Because now you can talk about comparing variability of two totally different measurements. Height, centimeters, weight, kilogram, but their CV. So generally, for example, in humans, height has about 15% coefficient of variation. Okay. So coefficient of variation is very useful for comparing across the board. Now, साजिद अली साहब ने कहा कि भाई समझाओ बच्चों को कि सुनने वालों की हाई वेरिएबिलिटी क्या होती है, लो वेरिएबिलिटी क्या होती है. What is high variability? There is no definite answer, but as a practitioner, I will give you some thumb rules. So 10% is low variability. CV 10% is low variability. CV 30% is moderate variability. CV 60% is high variability. CV 100% is very high variability. Kuch gadbad hai. Huh? What was the CV for the one-day-old chick? Weight to 6.1%. extremely uniform. Not much variation at all. Because there's the same breed, everything. Okay. Next, where do you expect low variation? So in fields like physics and chemistry, variation is very low. In engineering, variation is much lower. In biology, variation is higher. Worst story is psychology, sociology, so high. But what to do, boss? I have to live with it. That is the phenomenon I'm studying. I can't complain about variability. All right. Now, now it looks like this is really not necessary because you have seen displays of SPSS and so on. But since I have prepared the slide, I will quickly go through it. So now I am showing some displays of outputs for mini-tab for comparing two groups. So A1 and A2 are, remember, two groups of one-day-old chicks, and we are raising a hypothetical question. Is the mean weight the same? And look at this. First group has mean 40.25, second has 38.8. If you recall those box plots, I said, is the second group thinner? Is the difference between these two significant, or is it due to chance? Or can we treat it as zero? So mathematicians write it as mu A1 equal to mu A2. Badi baat nahi hai. The difference between means is 1.45. Now this is probably another thing which was not introduced in earlier lectures. So typically you will find in outputs confidence interval. What is a confidence interval? So you see, I told you that biological results are not easily replicable. If you took a bunch of 20 one-day-old chicks and still another bunch of 20 and looked at the difference, that difference will not be 1.45. How much will it be? It could be more, it could be less. But based upon the standard deviation and normality, etc., mathematics shows that the difference will be somewhere in between, minus 0.27 to 3.7, based on this data set. Okay? So, confidence interval is a range of possible values if you repeated the same experiment. This is the idea. Okay. It shows how things will change in repetition of experiments. So now, what is it that we are testing? We are testing that the difference between means is zero against an alternative that it is not zero. This VS is supposed to be versus, not equal. Equal versus not equal to zero. And you get a p-value. So this p-value is 0.097. When you write a paper, you will have to quote this p-value. Okay. And what do you do with it? What is the conclusion? The general principle is if p-value is very large, then null hypothesis is okay. If p-value is very small, null hypothesis is not okay. That means the data go against the null hypothesis. Are very small matlab kya? What is small? So Dr. Gite yesterday was using the value 0.05. And I want to tell you that is just a convention. You feel free to decide what is the p-value below. You have to select a threshold. जिसके नीचे जो है अपन null hypothesis reject करें. Okay. 0.05 is the convention. Now I am going to recommend something slightly different. I am going to say there are different kinds of experiments. Exploratory experiments. Typically, for example, in clinical trials, you have molecules. Initially, there are many competing molecules available. And you just want to discard things which are useless. At that time, p-value for threshold is about 10%. Anything more than 10%, so you discard. Anything less than 10%, that difference is significant. Whereas when you go to the FDA regulator, at that time the p-value has to be very small. Now, I'm not sure, in some situations, maybe 0.05, maybe 0.1. So I want you to realize this p-value fellow will be given by software. You have to copy it, you have to reproduce it in your paper. But you have to be careful. There is no mechanical way of interpreting. you can pick a threshold. So you will say, by TK, how do I pick the threshold? Go to the journal in which you are publishing, and you will see some papers, whatever is the typical threshold they have selected, you should select the same. And then what is this DF? That is degrees of freedom. Degrees of freedom simply means how much are the bits of data you already have. See, already we have 20 and 20, 40 data bits already. We have estimated something. We have estimated these two means. And we have estimated, we assume now that the variance is the same for both. You remember Levines test, if variance not equal, it checks it. And if not equal, you have to do something. Generally, variances are equal. Then you have to estimate the common variance. So the mean of first, mean of second, and common variance. Three things estimated. Out of 40, 3 degrees gone. Whatever remains is 37. This is roughly what degrees of freedom are. I would not recommend you to get too much deeply into it. You should. Software will give you the value. Stick to it. Report it. All right. So now let us take a case of non-normal. Okay. That lady said, show us where things are different. Okay. So here creatinine is being measured. And look at the histogram, look at the normal curve, and you can judge for yourself. Does it look normal? My recommendation is apply the test of normality. And in this case, the p-value is very small. So this is not normal. Okay. So what do? We use non-parametric test. Non-parametric test checks median, and for the two groups, the median was, sample value of median was exactly the same. So abhi kya test mein karne ka hai? So the difference in medians is 0 in the sample. So what is the confidence interval? Minus 0.1 to plus 0.1. Okay, p-value is 0.5, so it is very large, and we will not reject the null hypothesis. The null hypothesis was there is no difference. Difference between what and what? Measurement with and without ultrasonography. Or evaporate. If there is no difference, why waste time and money and everything on ultrasonography? Whatever was the traditional method is good enough. That is the implication of this test. Okay. So if you are doing an experiment or a series of studies, at this point you say, because of this evidence, I have decided not to use ultrasonography. You will be justified. It does not mean that ultrasonography is not useful anywhere. It simply means that the context in which you tried it, it is not giving you any value different from the traditional method. But don't condemn a new method quickly. Maybe there is some other measurement where it makes a difference. So instead of creatinine, let us take some another chemical. Oh, in between. So there is the two sample problem and the paired sample problem. In this case, I think it was not clear, or we didn't have enough time to sort out. One measurement is given under ultrasonography, one without. Are these the same specimens? Same experimental unit, same animal, or different animals? If it is different animals, then you get two sample t-test. If it is same animal, then they are not independent. Then we work with differences. So it's called paired values. But so let us take another protein, and this was AST, so I don't know what AST is. I did not take the trouble of going to Wikipedia and looking up what is AST. So I looked at the difference, and do you see here, the blue line goes one way and these red points are going whichever way they want, and the p-value is very low, 0.048. So this is also a case of not normal. Okay. So now what do I do? And yesterday, I think Dr. Gite explained to you Wilcoxon signed rank test. So we can use the signed rank test. And what does it test? It says that the differences have median 0 versus median not equal to 0. And here the p-value was 255. Quite large sample. Estimated median is 1.7, but it says 0 be okay. Meaning the difference between this presumed 0 median and this sample median, this is due to chance. All right. So we have confirmed that even for this second chemical, ultrasonography does not seem to make any difference. So these are the kinds of uses to which statistical inference will lead. If you have 3 or more groups, then you need to do ANOVA. ANOVA means analysis of variance. Let's not go into that. If you have 2 groups, t-test. If you have 3 or more groups, again normal equal variance, then use ANOVA. Okay. So let us take a case where we know there is no difference. So 3 groups of 1-day-old chicks. They are all same. One-way ANOVA. This is the output of the Minitab software, and it gives something called the analysis of variance table. And we don't have to go too much into details, but the p-value is 0.9. So whatever differences are there are due to chance. No difference. This is how we use ANOVA. And the last thing before I end, I have another 10 minutes and then I will stop. Studying two variables. This was also a point that was raised by Dr. Gite. So there are 2 different variables. For example, effect of diet on body weight. So you have diet and body weight, or number of study hours and exam marks. And then you can calculate Pearson correlation coefficient. Yesterday he showed you all this. And the correlation coefficient is between -1 and +1. And if it is closer to 0, there is no relation. If it is closer to plus or -1, then strong relation. If it is closer to +1, it means positive relation. One goes up, the other goes up. If it is closer to -1, negative relation. One goes up, the other goes down. Trivial example of a perfect correlation +1. Onion is 20 rupees per kg. I am buying 15 kg. How much is the money? The money to be paid is equal to 20 into weight in kg. Simple. Okay. And the correlation will be +1. Perfect positive correlation. Here is an example. Ambient temperature, as it goes down, sale of sweaters goes up. This is a negative. One thing goes down, the other goes up. This will not be perfect. Some people will not buy sweaters, some people will buy many, whatever. It will be a negative correlation, but it will not be a perfect correlation. Okay? Now, what is it that interests me? Growth of body weight. So on x-axis, I have week. On y-axis, I have the average body weight. Okay. This is the data from Sajid. What does it say? As expected, as time goes, if everything is fine, then body weight will go up. In this case, correlation is very high. Okay. Positive correlation. Now, when something works, your ambition goes up. Now I want to fit an equation so that I can predict what will happen 1 week down the line, 2 weeks down the line. And that's the regression equation. So weight in gram is equal to -0.95 plus 237 times the week number. So this 237 is the coefficient. It's called the slope. So y equal to mx plus c. This is m, this is x, and this is c. Okay. Now I can plug in week, 10th week, kitna hoga weight? So 23710 multiplied by, 237 multiplied by 10. And what did I get? Can I do the same thing with 100 weeks? This equation would have given me 2.27 kilograms at the end of 10 weeks. This also may be on the higher side and maybe, in fact, but to make the point ridiculously obvious, can I put week number equal to 100? Then I will get 23 kilograms and more. Is this possible? No. See, we were talking about using a regression equation to forecast. But I have given you a red flag. What it says is, you can't plug in any value you want. just a little bit beyond what data you have observed. If you have observed 6 weeks, then 7 week tak theek hai, 8 week tak theek hai. Abhi 10 week ka bhi mere ko lagta hai ki zara, it's not giving a reasonable answer. 100 week obviously is a foolish answer. If you said to anybody that my 1-day-old chicks in 100 weeks, matlab kitna ho gaya? 2 years, they will become 23 kilograms. They will laugh at you, kick you on the butt and throw you out. So what is the message? The message is, this is called extrapolation, going beyond what you have observed. So if you have a regression equation, it is good enough for just a little bit beyond where you are. If you go very far, useless. You will get some foolish results. You will come to hardship. So forecasting is important. It is useful. But the first important lesson is, don't forecast too much into the future for many reasons. Again, we won't go too much into that. So what do you think was happening? Why even at 10 weeks, I was getting answers which were unreasonable, obviously totally wrong. What happens is, after a while, things plateau. See, this is an assumption of linear relationship. It holds only in a small range. After that, it doesn't hold anymore. Okay. So in this case, our correlation was very nice. The data points are very close to that line. So for this observed portion, the equation is nice. And for intermediate values also it is equal. But 2.5 weeks, all that you can easily get. But don't go too far beyond. The question is, whenever you have X and Y, will you always get good correlation and always get a good regression? And I want to give you an amazing example. Why I call it an amazing example? Because in my entire career, I had never come across such a good example. So, you see, I take these 1-day, 2-day programs to motivate the students and prepare them for industry. So, this program was in a very small town named Y. It was a small college and a small statistics student group. And usually, I told you that statisticians are not taught extension. So I try to teach. I say, get up, don't warm your seat anymore, leave. Just as agricultural scientists go to farmers, doctors go to patients. What about statisticians? They should go to other biologists who generate data. So I said, go to other biology departments in your college and get data. And they got this data. I was astonished. And you will see why I'm saying this. So what are the data? This is about germination rate of sorghum and mung beans. What is the principle? What is the thinking of this man? He says that germination rates, there will be a natural germination rate, genetic property. And then depending on the environment, and what do you mean by environment? He's talking about toxic element. See, for germinating, these seeds will be kept in water. To that, if you add some toxic substance, then germination will be affected. This is the idea. And his whole PhD thesis was concentration of toxic substance and source of toxic substance and so on and so forth. So this is one data set. So control, what does it mean? It means that if you took the mung beans and put them in water and whatever, I don't know, 83% germinated. Then what is this 0.5? This is the leachate concentration. So this toxicity comes from leachate of Argentina leaf. Agraratina leaf. I don't know. So it is looks like a poisonous plant. So if your concentration is 0.5%, 2.5% from 83, it goes down to 80. So the idea is that if there is too much toxicity, gradually the germination percentage will fall. Okay. But his interesting thing is, remember in scientific research, in journalism, if a dog bites a man, it's not news. It is news only for the man's wife, the man's mother. If man bites a dog, then it's news. So if toxicity reduces the germination percentage, that's not news. But if toxicity increases the germination percentage, that is. So here you see from 83 to 88 it went up. 92 it went up further, 97. Then it started falling. So his point was that at very, very low concentrations, substances which are considered toxic otherwise can actually help. Okay. See, in homeopathy, they have this principle. Whether to accept homeopathy is a different matter. I'm just drawing a parallel. That they use those poisons as medicines in extremely dilute form. Whatever. Okay. So this is the data now. So what is our X and what is our, we are talking about correlation, two variables. Toxicity percentage in water and percentage of germination. These are the two variables. And general idea is high toxicity means lower germination. Eventually everything will die. But his idea is at very low level, it may help. Can regression help here? Look at this data. You think we should draw a straight line through these points? Stupid. Only statisticians do such things. A biologist will say, "Nahi, kya hai? This is not linear." Right? What are we trying to do? We are trying to give an example where linear regression does a bad job. Right? So let us overrule reasonable biologists. Ye linear nahi hai. We will impose our will. Linear hi karenge. Does it not? Does not look linear. We insist on linearity, okay? Just to prove a point. Kya hoga? The equation we got was germination percentage 90.2 minus 1.91, whatever. What is the correlation? It was 0.23. Earlier we got 93.95 correlation. It is 0.23. Very poor correlation. Not useful. It is quadratic curve. Okay. What is the quadratic curve? Y equal to A plus Bx plus Cx square. So it is A plus B into leachate concentration plus C into leachate concentration square. Okay. We can fit that. And we got this equation. What have I plotted here? Observed values of percentage germination on x-axis and values given by equation on y-axis. And they are pretty close, not exactly equal. That you don't expect. Quadratic regression equation gives a good performance. Okay. What if both on the same? So this last graph, so let me revisit this graph. What is this graph? On X, for each case, I had an observed value of germination percentage. And there is a leachate concentration. By substituting that leachate concentration into the equation, I get an expected or estimated percentage. So estimated value on y-axis, it is called fitted value. That's why this has a name fit. And observed value on x-axis, if observed and expected are perfectly equal, then that means my equation is perfect. This is not perfect, but very good. Now what I'm going to do is not like this, slightly different. Oh, incidentally, 91% is the R square. So roughly speaking, most of the variation is explained. This is very good. Now what is it? On x-axis, I have simply serial number. Leachate concentration, some kind of notation. On y-axis, I have. So the blue values are the observed values and red values are the equation. So I hope you see that our quadratic equation does a fantastic job in this case. And I found that the linear Pearson correlation is very poor. Quadratic equation does a fantastic job. So sometimes you have situations like this. So what do? You have learned how to calculate correlation and use it. But I am saying linear regression. If it doesn't work, you can do something else. All right. No matter how much anybody teaches statistics, when you start actually using it, you will face difficulties. Maybe this point was made earlier, probably by Dr. Samad, that you should discuss all these things amongst yourselves and your statistics colleagues or consultants at the planning stage. Don't do it at the end. Then corrective steps are very difficult. If you have problem while planning, if you have problem while designing an experiment, if you have problem in planning a sample survey, in data analysis, model building, you should approach your local statistician in the college nearby, university nearby, or as long as I am active, feel free to approach me. So once again, let me give you my email, and my time is nearly up. So my hosts have been, they have not allocated me. I think I am close to finishing my time. So with 10 minutes to spare, I will conclude my lecture. I will say thank you very much for this opportunity. Having to prepare this lecture has been very educative for me, and attending all your lectures so far has also been very educative for me. So thank you very much. Dr. Nandedkar, Dr. Sajid Ali, I am finished.
Yes, sir. Thank you, sir.
Sure.
There are some questions.
Yes. So let me open the chat box. Oh, last slide, repeat. Arey bhai, you will get it from Dr. Sajid Ali. He has all the slides. Huh? Book slide also, Sajid Ali has the book slide. So, the only reason I am not, because it will take time. Not audible, I am very sorry. I didn't realize that I was not audible to some people. How we select attributes or weigh variable factors. So please don't expect statistics to solve your biology problems. You must be able to identify what you are measuring, why you are measuring, what is the purpose of your experimentation. I don't think this is a statistics question. This you have to sort out. What is the difference in testing significance on the basis of t value? And t is simply the, see, what is this t fellow? They say if you have two groups, you take the mean of the first group, mean of the second group. Are they different? By and large, they are different. Question is, are they too much different? So they create this t ratio. So it is simply the statistic to decide whether the difference is too much or it could be assigned to chance. And that answer is in p-value. So you are going to use the p-value, not the t as in Tom, but p as in Pune. P-value is what is important for you. While designing experiments, how do we weigh the factors or select attributes? That you have to answer yourself. I'm happy, I'm open to discussing biology questions also, but that is not a statistics question. What is one tail and what is two tail? Excellent question. So I am giving an additive to the diet. When will an additive be useful? If weight goes up, right? So I have control where people get, or chick gets normal diet. I have treatment in which normal diet plus my additive. If this is the case, what is the question I am testing? I am saying additive ka kuch fayda nahi. This is the null hypothesis. That means the weight of the chick with special diet is same as weight of the chick as the ordinary diet. What is the alternative? Alternative is that with my additive, the weight goes up. Earlier we said these are equal or not equal. Equal, not equal ko bolte hain two tail. Whereas if I am deliberately trying, my intervention is for increasing, then I better look whether it is increased. So this is called one tail. So it is all a matter of, don't go by tail. It is all a matter of what you are looking for. Now you want to decide normality. What is the cutoff? I would say use the conventional cutoff 0.05. उससे भी कम हो गया ना तो बोलो ये नॉर्मल नहीं है. 0.051 हो गया तो क्या बोलोगे? So it means your threshold is crossed, but don't be too comfortable. Normality hai, but these are not clear. Biologists have this wrong notion. The statisticians are always able to give them yes, no answer. नहीं है. Tendency. तो टेंडेंसी 0.051 p वैल्यू है ना तो हम बोलेंगे यार थोड़ा नॉन नॉर्मलिटी है. सो दीज आर हेजी डिसीजंस. कंफाउंडिंग इन फैक्टोरियल एक्सपेरिमेंट्स. बॉस ये थोड़ा टेक्निकल हो गया. दिस इज ए मोर टेक्निकल क्वेश्चन. Confounding means you are not able to separate out effect of this and effect of that. That's called confound means confusion ho jata hai. That is a more technical question. If necessary, we can take it offline. For this entire audience, I think this is not the right lecture to talk about confounding. It's an important issue, but not right for this class.